Here's a question to try to understand the distribution of prime numbers in the number line. In particular, to try to understand how many numbers you need to sort of like cover most of the natural numbers as multiples of one of the first n prime numbers. So for example, if you just take the prime number 2, 50% of all numbers are even. If you take the primes 2 and 3, then 66% of all numbers are already multiples of 2 or 3. If you take 2, 3, and 5, then that goes up to 73% of all numbers are a multiple of 2, 3, or 5. So how high do you have to go so that you cover 95% of all numbers as a multiple of one of the first n prime numbers? So here are the options. So I ran this poll in the Bird app just to see what's the intuition of most people, and most people thought that 40 primes would be enough. And it turns out that the correct answer is 4,000, which is the one with the least number of votes in the poll. Let me show you some data. So let P of n be the function that models this. So P of n is the proportion of natural numbers between 1 and 10 to the 10 that are divisible by one of the first n prime numbers. So P of 1 is 50%, P of 2 is 66%, P of 6 we're up to 80.8%. Here's the graph, by the way, of P of n, which I did with CoCalc, with Sage Math, and you can see that it grows at first very fast, but then it starts to grow very, very slowly. And then you can see that by 40 primes, we're already almost at 90%. So 90% of all numbers are a multiple of one of the first 40 primes. However, the function keeps growing very slowly after that, and by 55 we reach actual 90. By 400 we're still at 92.9%, and it's not until 3,881 primes that we reach 95%. And then it keeps growing very slowly after that. By 4,000 we're only at 95.02%, and by 40,000 we're at 95.4%. The values of this function P of n, by the way, you don't have to go one by one counting through the numbers from 1 up to 10 to the 10 to see which ones are multiples of which. There are ways to accelerate that process using things. For example, using the Euler phi function, you can find approximations of this function, and even better, using something called the Legendre formula or the partial sieve function or Legendre sieve. You can count values of this function P of n very quickly. And that's how I've actually computed that graph using Sage Math or CoCalc, where you can implement this function, and that's how I created the graph. So anyway, my takeaway is that essentially the first 40 primes is enough to cover about 90% of all numbers, so a lot of it. But then to cover more holes up, you have to go sort of prime by prime, and you need a lot of primes to cover those small holes that are left in the number line. And those small holes are precisely where the prime numbers end up being as you go along. And that distribution of those holes, the distribution of where the prime numbers are, is why we are so interested in things like the Riemann hypothesis, which gives you very precise information about the fine elements of the distribution of prime numbers.